Okay, here we have another example of representing a surface parametrically. Write a set of parametric equations for the cone given by z equals the square root of x squared plus y squared. Here's a quick sketch of the cone. If you square both sides of this equation, you get z squared equals x squared plus y squared. Since this surface is given in the form of z equals f of xy, you can let x and y be the parameters. It's not always necessary to introduce those parameters u. You can let x and y be the parameters. And again, if you let x is equal to x, y is equal to y, and then use that what z is equal to, you can now say that this is your vector valued function r in terms of the parameters x and y. Let's begin by talking about normal vectors and tangent planes. Let S be a parametric surface given by r in terms of u and v equals x of u and vi plus y of u and vj plus z of u and vk. Now the partial derivatives of r with respect to u and v are as follows. To find the partial derivative of r with respect to u, you're going to take the derivative of each of the components, treating u as a variable and v as a constant. When you take the partial derivative of r with respect to v, you're going to take the derivative of each of those components, treating v as the variable and x and u as a constant. Now, each of these partial derivatives can be interpreted geometrically in terms of tangent vectors. And this is what I mean. You have a surface and you calculate the partial derivative with respect to u and v of some surface, some parametric surface. What you've done is you've found these tangent vectors. And these two vectors are tangent to the surface, and this vector n is orthogonal to the surface. And the way you calculate that orthogonal vector n is by finding the cross product of RU with RV. If the normal vector, as long as that normal vector is not zero, then this surface S is called smooth and will have a tangent plane. You can find a plane that just touches the surface at that one point and is tangent to the plane. So here again, we're looking at a normal vector to a smooth parametric surface. You have your parametric surface R in terms of u and v, and you're looking at a given point, x sub 0, y sub 0, z sub 0. Then calculate the partial derivative with respect to u, cross product with the partial derivative with respect to v, evaluated at that point given in terms of u and v, and that vector is going to be normal. Remember, the cross product always results in another vector, and that vector is going to be normal to the surface. And if you have a normal vector, you can use that to find the equation of a tangent plane. Again, to find the equation of a tangent plane, you need a point and a normal vector. In this example, we want to find the equation of the tangent plane to the paraboloid given by r in terms of u and v equals ui plus vj plus u squared plus v squared k at the point 1, 2, 5. To find the equation of a tangent plane, you need a point, which is given, and you also need a normal vector. To find that normal vector, you're going to take the partial derivative of r with respect to u and r with respect to v. Now in this case, x is equal to u and x is equal to 1, so u is equal to 1. Y is equal to v, and at the point y is equal to 2, so v is equal to 2 at that given point. So it is important that when you're given the point, your point is always given in terms of x, y, and z. But when you're plugging in values into the parametric surface, you're plugging in values for u and v. In this case, it's a direct correspondence between x, y, and u, v, but that is not always the case. You will have to solve for u and v given the x, y, and z. When you find the partial derivative of the vector valued function with respect to u, you're going to treat u as a variable, v as a constant, so that partial with respect to u is equal to I plus 2uk. And Taking the partial of r with respect to v, treat v as a variable and u as a constant, and that partial derivative is j plus 2vk. You can plug in the value for u and v, which is 1 and 2, to find those vectors, and then you can find the cross product of those to find the normal vector. When you can set it up this way, find the cross product of u and v to get this, and then you can plug in the value, let u equal 1 and v equals 2, and you find that this vector negative 2i minus 4j plus k is the cross product vector, and that vector is normal to the surface at the given point. So to find the equation of a tangent plane, you need the point and the normal vector. The normal vector components are the coefficients, and you use the points by subtracting. You get negative 2 times the quantity x minus 1, minus 4 times the quantity y minus 2, plus the quantity z minus 5 equals 0. Which is simplified to negative 2x minus 4y plus z equals negative 5. And this is a plane. This plane is tangent to the surface at the given point. This little pink shaded region is a representation of the plane that is tangent to the surface at the point. Okay, try this example on your own. Given the parametric surface R in terms of u and v equals ui plus vj plus the square root of uvk, find the tangent plane at the point 1, 1, 1. You want to find the partial derivative of r with respect to u, r with respect to v, and find the cross product of those. That's going to help you find the normal vector to the surface at the given point. Try this one on your own, pause the video, and then come back and check your solution. Okay, let's begin by taking the partial derivative of r with respect to u, treating u as a variable and v as a constant. Derivative of u is going to be 1i. Derivative of v we're treating as a constant, so that's going to be 0j. And then the square root of uv, well, think of this as uv all to the 1/2 power. So when you take the partial derivative with respect to u, using the chain rule, it's going to be 1/2 of uv to the negative 1/2 power times the derivative of what's inside with respect to u. The derivative of u times the constant v is going to be v. It's going to be your k. When you simplify this, you get 1i plus 0j. I'll go ahead and write that anyway, you don't have to, plus d over 2 square root of uvk. Now let's take the partial derivative of r with respect to the variable v. Treating u as a constant and v as a variable, the derivative of u is going to be 0. The derivative of v is going to be 1. And the derivative of square root of uv is going to be 1/2 of uv to the negative 1/2 power times the derivative of uv, treating v as a variable, u as a constant. That's going to be uk. When we simplify that, it's going to give us 0i plus 1j plus u over 2 square root of uvk. Now we want to find the normal vector. The normal vector, which is found by taking the cross product of r, partial of r with respect to u, and the partial of r with respect to v. Okay, and you can go through and work out that cross product. And you will get negative v over 2 square root of uvi, comma, or plus negative u over 2 square root of UVJ plus K. And you can work that out by expansion by minors, finding RU crossed with RV. Now we want to figure out what to plug in to this to find the normal vector at the specific point given. For our parametric equation here, we have x is equal to u and y is equal to v. And at the points, we have x is equal to 1 and y is equal to 1. So that means we're going to substitute, we're going to let u equal 1 and v equal 1 to find the normal vector at the point 1, 1, 1. That normal vector, when you plug in 1 for u and 1 for v, is going to be negative 1 over 2I minus 1 over 2j plus k. So we're going to use the components of your normal vector as your ABC for the equation of the plane. Again, recall the equation of a plane is found by taking a times x minus x sub 0 plus b times y minus y sub 1 or y sub 0 plus c times z minus z sub 0 equals 0. When you plug in the a, b, and c that we found using the normal vector, we get negative 1/2 of x minus 1 minus 1/2 of y minus 1 plus 1 times z minus 1 equals 0. Again, we've used the components of the normal vector and the given point to find the equation of the plane, which can further be simplified.